Thank you very much. And thanks very much for putting together this nice event and for inviting me. So I was kind of inspired when I read the text on the website, which was something about pulling together people from different areas and trying to gain inspiration, in particular things of like how invariants in one place have inspired invariants in other places, where there's a bit of an emphasis on Vaughan-Jones's like theory of subfactors that really was the inspiration for the Jones polynomial. And while I'm not going to define a new Jones polynomial or anything of that sort, I was kind of inspired. I was inspired to that. So I had these ideas, some now what 4 years or something like that ago, and I just I'm like a dog chasing a squirrel when I'm doing maths. I do something and then I just suddenly get interested in something else, and then I haven't actually thought about this for like 4 years. And I figured maybe I should talk about it. Maybe that will inspire some more work to be done in this kind of direction. So let me just try to set up the stage with what kind of inclusions of C-star algebras am I thinking of? Because really what I'm thinking of is just one C-star algebra sitting inside of a different C-star algebra. But what would be some good examples to maybe keep in mind? So the first example is one we've seen plenty of times already, which is if we've got G is an Ital groupoid, then we've seen that the continuous functions on the unit space sit inside of the reduced groupoid C-star algebra as a C-star subalgebra, and this will be one of the motivating examples that I'm going to be considering. But so, like, spoiler alert, I'm not really a groupoid person, and usually when I think of groupoids, whenever people say let G be a groupoid, I'm secretly thinking of either a group. Or maybe I go a bit exotic and do a transformation group. And then those are going to be my second source of examples, because if you've got G is let's say a discrete group, we've got some, let's say X is a compact Hausdorff space, and we've got some action G on X, then we've seen already, I think Aidan mentioned this in his talk, that we can construct a groupoid again, which is the transformation groupoid, which essentially consists of triples of this form, where, well, I guess in this case, X equals GY. So obviously the X is kind of redundant, but it makes it nicer to think about it in this way when you're actually working with these things, to think of it as triples instead. So have I just given another example of a groupoid? That wasn't really the intention I was going for. I want to consider a different C-star subalgebra in this case. And one way of constructing this, I think very much in C-star theory. Like, for me, I have to think in C-star algebras and then translate it into groupoid language, which is what I did when I was preparing the talk. So if you've got, so every group element induces a compact open bisection in this case, and let's call it UG, where UG is just going to be all the triples of the form GX, G X, where X runs through X. So you get this nice family of compact open bisections in your groupoid. And one thing we can do is we can think of the reduced group C-star algebra, so just doing the reduced groupoid C-star algebra, but with the group. This is just the C-star algebra generated by these, oops, I shouldn't say, I should say the indicator functions on these compact open bisections sitting inside of the groupoid C-star algebra. So I consider this as being an example where instead of just considering the groupoid and inducing a C-star algebra, I take a groupoid, but then I also remember a bit more of where did it come from? Like where did it came from this group? It was constructed as a transformation group. For the C-star algebraists, like the way I would really think about this is that this is a cross product C-star algebra, which means it's generated by a copy of C of X and a copy of the reduced C-star algebra. Kind of like how you do a semi-direct product of groups. All right. So these kind of examples are also all over the literature. And for instance, a good example was in some of the work of Callender and Kennedy when they were studying C-star simplicity. So one crucial ingredient there, so they were trying to characterize when are these groups, these C-star algebras, sorry, when are they simple? And if one crucial ingredient for them for characterizing simplicity was that if X is a G boundary, and please don't ask me to define what a G boundary is. So this could, for instance, be the Furstenberg boundary, which is their prime source of examples. Then they, for instance, show, and then I say they, that's Callender and Kennedy, they showed that C star, oops, reduced G is simple if and only if the groupoid C star product is simple. So here are some examples where you've got these inclusions of C-star algebras appearing naturally from, say, things like groupoids or group actions.
Can I ask you a very small question about the G boundary?
I will not be able to answer it, but go on.
So if X is a G boundary, does that include implicitly that X is being acted on by G?
Yes.
Okay, so this action is automatic and it's not, or it's part of the information.
I could answer it, and yes, yeah. I meant the action of like on X is a G boundary. All right. So this was supposed to be something about invariants. So I'm going to talk a bit about invariants for inclusions. And one thing, so when I started out my PhD, I started out doing graph C-star algebras, and I was very happy doing graph C-star algebras. And then I started classifying graph C-star algebras. And before too long, I had gone very deep into the classification program. And what are we considering? What kind of invariants do we consider in the classification program? It's already come up plenty of times. It's K-theory. So let me just, I know that not everyone in the audience are too familiar with C-star algebras, and even though we've already seen a bit of K-theory, I just want to make sure that everyone knows what K-theory is and just get people on board. So for the purpose of this, I'm going to assume that A is a unital C-star algebra. If my C-star algebras are not unital, it's a bit more fiddly, but not that much. So what is the study of K-theory? Well, to sum it up very roughly, it's about projections and it's about unitaries. So a projection, it has already come up several times, is an element in a C-star algebra such that P equals P star equals P squared. And this is really just, if you're thinking of A as acting as bounded operators in a Hilbert space, this is just an orthogonal projection into some subspace of the Hilbert space. So we say that two projections are equivalent exactly when there exists some partial isometry in the C-star algebra. This is a partial, these are called partial isometries, such that V star V equals P and V star equals Q. So these partial isometries are going to play a crucial role in a moment, also for the people who know K-theory. I'll probably turn the K-theory into something you haven't seen before too long. Don't worry. So, wow, don't fall asleep is what I should have said. So, first of all, when you want to define what K-theory is, or K0, you want to do what Enrique was doing in his talk and look at a certain monoid first. So the monoid I'm going to consider is that I take the union over all the projections, the set of all projections in matrix amplifications of my C-star. So if I have like a 2x2 matrix, I can consider it as sitting inside of the 3x3 matrices by just adding a bunch of zeros, and so on and so on. So I look at the union of all of these modulo equivalents, which is the same as Murray von Neumann equivalence. Or it's called Murray von Neumann equivalence, but this equivalence relation could also be replaced with things like homotopy, for instance. So this gives us an abelian monoid. And then, in order to make it computable, we take the Grothendieck construction of this. Oh, I forgot to mention what's the monoid structure. If I want to add two equivalence classes together, I just stick them as orthogonal, like, complementary corners in some matrix. So the K0 group of A is just the Grothendieck group of this abelian monoid. So you're just looking at formal differences of these type of things. The K1 group is easier to define. So for K1, we consider unitaries, and a unitary is of course just an element U such that U star U equals U star equals 1. And K1, the C-star algebra, is just, you take again a union over matrices, and then you look at the unitaries inside of the n by n matrices again. And this time when you're enlarging them, you want to keep a unitary, so you just stick a 1 down in the corner every time you enlarge these things. And then you quotient out by homotopy, and now we know K-theory. So this is what K-theory is. It turns out that K-theory is often computable through certain methods inspired by things from, say, algebraic topology, like long exact sequences and such. You could also say, like, you've got K0 and K1, what about K2, K3, K4? But it turns out that these are periodic. So K2 is the same as K0, and K3 is the same as K1, and so on and so on. What does this have to do with inclusions? That's what I'm coming to now. So when we've got an inclusion, we can look at what's called relative K-theory. And the theory of relative K-theory is somewhat scattered / implicit in the literature. I asked Kuntz about it at some point, and he was just like, but that's obvious. But you can also find things written in more detail by, say, Ian Putnam, even though he doesn't do it exactly in the way that I would, that I'm going to present it here. So now, if we take some inclusion of C-star algebras, and in this case, so before I was looking at unital C-star algebras, so I'm going to take a unital C-star subalgebra. So I've got a unital C-star algebra and a unital C-star subalgebra. So they share the same unit. What I'm going to do now is I'm going to define a similar, a construction of K-theory, or something that looks very similar to what I've just defined for you, but it uses both A and B. And this is what is often referred to as the relative K-theory. So for the relative K0 group, what I'm going to do is I'm going to take, again, a union just like before, so that we can do these diagonal sums as our sums. Then what am I going to take the union of? I'm going to take these elements in my n by n matrices over my big C-star algebra.
Does B stand for big?
B could stand for big, yeah. Let's say that B stands for big and A stands for
big.
So what should be satisfied by this V? Well, I've already talked about projections and unitaries. Note that just as a fun little side remark, because that will actually play a little role in a moment, these unitaries are examples of partial isometries. We're basically going to fuse these two things together of like projections and unitaries in terms of these partial isometries. So V should be a partial isometry in the big C-star algebra, such that these projections, these V, V star, and V star V, they land in the subalgebra. So you take this thing, then you quotient out by homotopy, and it turns out that quotienting out with homotopy isn't quite enough. So what we also want to do is we want to consider just a projection in A as being a trivial thing. So you could also say just a projection, take V to be a projection, that should also be considered as a partial isometry, but those we kind of want to quotient out. So we also add, like we quotient out by all projections in, it's implicit that I'll have to land B in the small one. And this thing here, again, becomes just like before. The two other things became abelian groups. I didn't discuss that K1 was an abelian group, but it is. This thing also becomes an abelian group. The inverse you can just represent by V star. Flipping things around. So just as a little side remark, just to tie it a bit into the groupoids, is that I actually prefer to think of V not just as a single V, but as a triple. I like to think of it as being triple V star V, V, V star, V, V star V. So I'm thinking of it as being the middle thing that kind of points between these two projections. Like very similar to how we've got this thing up here. This isn't really relevant, it's just how I think about it. Because it also helps you thinking of how can you, it simplifies how you work with them, for instance, again, kind of like how I like to add the extra X up here. So
question.
Yeah.
What do you do with the unit that is shared by the ring and by both algebras? I mean, it's a projection.
That counts as a projection, so it's quotient out. And what you should think about is it's in the same way as the unit in K1 is just 0.
Okay, because of the amount of it.
Exactly. Exactly. So we have some, the fun thing is that this thing is defined in such a nice way that we actually get some obvious maps that go from K1 of A, no, sorry, K1 of B into this relative K theory, which is just given by take a unitary and think of it as a partial isometry.
Sorry, James, what happens when A and B are equal?
When A and B are equal, this will always be true.
Right, so, oh, yeah,
Uh,
so it really wants to see the difference.
yeah, you really want these things to be different. If it had been if A had been the scalars, then it would be very, very close to just the K theory of B with a degree shift, I guess, or something else. That will follow in a moment from a 6-term exact sequence.
Is there a so the K0 when you just had one C-star algebra was made up of projections and adding them, or ultimately adding them, whereas this K0 is now multiplication of partial isometries?
It's like with K1. There you can choose, do you want to multiply them or do you want to add them diagonally? It becomes the same thing. And it's the same thing over here. You would define addition as being adding them in different matrix blocks, but if they turned out to be composable, it's an easy exercise to show that you can just shuffle these things around and then you just compose them the way you compose them. So you've got a canonical map from K1 of B to this relative K theory, but you also have a canonical map that goes into K0 of A, because if I took one of these partial isometries, I just map it to the difference of BV star and V star B. Because now I've got projections in the small. So I can also define, there's also a relative K1 group. I don't want to spend time on that one, but it's kind of similar, but a bit more tricky to define. So there's also a relative K1, but I'm not going to spend time on that. And what is, well, I would say, according to Kunz's folklore, there is an exact sequence which fits all of these things together. So we've got a map from K0 of A to K0 of B. We've got this relative, the map from the relative K0 group into K0 of A that I described up here. We've got a map from K1 B. These things loop around. We've got K1 of A. And then we can fit in this relative K group here as well. So we get this 6-term exact sequence. Yes.
You're looking for proof for that. Ian Putnam has a PhD student that did it in his thesis.
Yeah. But it is like you can, I would say it's you can, if you know how to prove that you get long exact sequences from short exact sequences of C-star algebras, you can just modify that proof and do something similar. So
is there a sort of an analog sort of relative K theory, and does these two actually coincide when we take AB to be like commutative C-star algebra?
I don't know. Maybe. Good question. I have no idea. All right, so where does this fit in with thinking about groupoids and invariants? I was pointing over here because I thought I had my groupoids. Yeah, they were here. They're gone. So the following that I'm going to mention is something that I did together with Christian Bünneker and Clement de la Hierra and Rufus Willett. It was really something that started out when I was a postdoc in Glasgow, and Christian Bünneker, who had just finished his PhD at the time, was visiting us, and he was a good friend of mine. So we decided we should do something together. We should find something to work on, and we were just like pitching things back and forth. He knew a lot about groupoids, I knew a lot about K-theory, and it was just like, haha. and this was like the start of what we then came up with. So I should say the following is joined with Christian Bünneker, Clement de la Hierra, and Rufus Willett. So in this case, I'm going to take a groupoid, because that was what Christian told me he wanted to do. So we took a groupoid which is second countable, Ital, Hausdorff, and ample. And ample might contain some of these words. I tend to lose track. Groupoid. So we take something, and just to make our lives easier, because I only described the case where we had a unital subalgebra, so I'm also just going to assume that the unit space is compact, but this is really not necessary. So what we realized, which I thought was a fun observation that I wanted to share with you, is that, well, when you're working with these ample groupoids, what are you usually really working with? You're so often, you always say, let U be a compact open bisection. And these are the generators essentially that you're working with. So I said, let U be a compact open bisection in the groupoid. Well, I've now got a compact open set of my groupoid. Well, I can look at the indicator function of this. So I can take the indicator function of this thing. So this sits inside of the compactly supported functions on G, which of course we think of as sitting inside of the reduced groupoid C-star. But what is this element from a more C-star perspective? Because I like to think about things in C-star algebras in terms of C-star algebras. Well, this is a partial isometry. So I can look at its class in this relative K group. And that's what we did. So we...
So the small algebras is continuous functions on unit space.
Oh, sorry. Yes, I forgot that. Thank you. So in this case, so the relative thing I'm going to do is, I should have mentioned this. So I'm going to take the A to be, well, continuous functions on G0. I'm not putting 0 since I assumed it was compact. And my B to be the groupoid C-star algebra. And the thing is, if I took this partial isometry in the groupoid C-star algebra and I look at what happens to, let me just call this V. So what happens if I look at V star V, I get chi of, damn it, source, thank you. And if I look at VV star, I get chi of range. And these both sit inside C of G0. And now it makes sense to say they give me an element in this relative K class, in this relative K group. So we get some reduced element in this relative K-theory class. K-theory. Well, that's all fine and good. Can we actually do something more? Well, we can go even further. We can take something that's built from these compact open bisections, which is the usual group ring, or groupoid ring, I guess. Which, well, I'm just thinking of it as an abelian group right now. So it is just a standard construction when you've got a zero-dimensional space, and even just any topological space. You just look at continuous functions from G to Z, but Z is a discrete group. So that just means locally constant functions. And then I also need them to be compactly supported. But this is really just generated in a certain sense by all of these compact open bisections. And this assignment that I mentioned here actually defines a homomorphism from this abelian group to this relative K group. So it gives us some way of constructing something. So what did we actually do with this? We were kind of like, well, can we actually say anything here? And as I was mentioning, Christian was a groupoid person, but he had gotten very, very interested in groupoid homology around this time. So Christian was explaining to me what groupoid homology was. I had no idea there was such a thing. And he showed me the definition, which is like, it looked so easy, and I was like, oh, that looks easy to work with. Like, what's the big deal? It turns out I had a lot to learn. So the groupoid homology for an ample groupoid, what you do, just to summarize it quickly, is you build a chain complex. You can also view this as a certain Tor group in the same way as you define group homology usually, but let me just do it, because the way I saw it, there is a canonical chain complex that you can use to define it, and it looks so nice and easy to work with, and I thought it was. But you basically just do this thing. You take all of the same construction I was mentioning before, but here we mean all the composable pairs, and over here we mean all the triples that are composable, and so on and so on. And going to G0, and then we've got these boundary maps between them. Let me call this 1. I guess if this goes to 0, I want to call this 0 and 2 and 3 and so on. And then I just define the homology. Like, this is a chain complex, so the homology group for the groupoid, and this generalizes a bunch of other homology theories or other constructions where you get an induced groupoid. Then you take the kernel of dn over the image of dn plus 1. This is what we were considering. So what we were working with before was this thing. It was part of the chain complex. Like, it looked promising. We have this chain complex where we can do something with homology. We had this exact sequence for these relative K groups. Because let me just add a second remark, which is this thing is isomorphic to the K0 of C of G0. So there was already some connection between these things, and that was what we wanted to explore a bit. At that point, that paper turned into much more of verifying the so-called HK conjecture in certain cases. But I'm not going to talk about that. What I will do is I will explain how does this fit in with what we did. Well, imagine that, so I've got this ZG0, and this surjects by definition to H0 of G. And we also had this isomorphism that I mentioned that goes to the K0 group of G0. And it's known that if I also look at the K0 of the reduced groupoid C-star algebra, well, then this actually induces a canonical map. Map is just take an element, lift it, map it down, map it to here, show that it's well defined. It is. But, well, we had more up here. We also had this ZG. It turns out, well, whenever I want to compute the homology of such a chain complex, I actually get a 4-term exact sequence that I can get out of this, where this thing goes into here. At a penalty, I have to quotient out with the same image that I quotient out with here, which is the image of D2. This here becomes a 4-term exact sequence. What we did then was, well, we took our relative K-theory exact sequence. We had these parts from this relative exact sequence. Let me just call it A, B right here, just to not write too much. And we had a map here, and we showed that it was killed on this subgroup. So we got a well-defined map here. Well, we continued the exact sequence. So now we get K1 of the groupoid C-star algebra, and we get K1 of C of G0. But C of G0 was totally disconnected because it was an ample groupoid, and well, you can either hit it with more hard-hitting theory, like it's an AF algebra, so it's 0, or you can just prove that it's 0 by hand. It's very easy exercise. This thing becomes 0, which means that this map here is injective, which means that we actually showed that there is a canonical map from H1 to K1. And this was only known in special cases before. And we showed that in favorable cases, like when we could say something about the HK conjecture, this map is an isomorphism. It took a lot of work. It was using a lot of triangulated category theory, and so we got a referee report back where we hadn't actually shown that we had constructed this map, we had shown that they were isomorphic, but they weren't the same thing necessarily. We got a referee report back pointing out the obvious thing that we had kind of dreaded, and we were like, oh no, and I already knew a bunch of triangulated category from when I was a master's student, and I dug into it and came up with this approach of doing it. And it turned out to be like ragingly wrong and not well defined what I had suggested. But immediately after I got COVID, and then I was in bed for 2 weeks, and when I got back, Christian and Clement had basically solved it. So that was good. All right. So this was. One could say that this was the theorem by Boedeker, Vinayera, myself, and Willett, is that there exists, let me say, a canonical map from the first homology group to K1, the C-star algebra, but it really uses relative things. It uses very heavily this interaction between subalgebras. So one of the reasons I wanted to talk about partially this was also, I do think that given how much we work with compact open bisections, I'm not sure if people were aware that they actually induce natural elements in these relative K groups. So I hope that someone might find that useful. So one thing that I use this for, and I hope that I've got time to mention what I want to mention here, but let me see. So there was a connection between homology and the topological full group, which has also appeared plenty of times during the conference, and there was a conjecture about how these things relate, and I realized that this conjecture, if you kind of think of H0 and H1 as being similar in flavor to K0 and K1 for the C-star algebra, it started reminding me of things I'd seen before. And this part of the talk is probably the part that I in my abstract described as more of a brainstorm. Because I want to try to explain this connection that I'm seeing. And I don't have any final theorem to go along with it, just here are some thoughts. And I'm already chasing many different squirrels right now. So I hope that someone might find this interesting and see if there's somewhere to go with this. So let me just recall that I'm still assuming the G is ample and probably other conditions, probably Hausdorff, because I still don't know how to work with non-Hausdorff groupoids. So we can build the topological full group. And what this is, in the ample setting at least, is that we look at all the compact open bisections with full support or whatever you would call it, which I just think of as being, so the range of U is the source of U, is the entire unit space. I'm still assuming this is compact for making this easier. And so what I did was that I put on my C-star glasses, because I do that most of the time, because I see compact open bisection and I'm like, what does this mean in C-star language? And what it really means is, well, if I look at the characteristic function, it's a unitary. Well, so what you're looking at here is some group of unitaries, essentially. But in the HK conjecture, which I'm not going to talk a lot about it, I should mention that Xin Li has solved a good chunk of it, and I looked up the paper and I did not understand a lot. I understood the theorem that said if the groupoid satisfies these conditions, one of them being comparison, which I have no idea what is, then it's this conjecture is true. But really what it does is there is this AH conjecture, which where there is a sequence which looks like this. You take H0 of the groupoid tensor Z12, you take the topological full group, but you want an abelian group because everything else is abelian. So you take its abelianization, and then you've got a map into H1, which I think Matsui calls the index map, and then to 0. And the AH conjecture says that if the group point is sufficiently nice, like minimal and effective, I think are the key words, then, and ample, I guess, then this is an exact sequence. So AH conjecture, this is exact. So this started reminding me a lot of something that I'd seen before. I think I realized this when I was in COVID lockdown in Australia, when I was a postdoc in Wollongong, and this looks like some of the ingredients that we use in what is often referred to as the new approach to classification. There's a new approach to these big classification theorems that I've been part of, together with Stuart White and Chris Schaffhauser, Aaron Seguisis, and Jose Carrion. And part of the invariant that we need to use, because we need more than just the usual Elliott invariant, looks a lot like this. So in which sense do I mean? So, well, as I said, we had some like group of unitaries essentially, and then we're taking the abelianization. This looks like something that we've worked with. So,
sorry, can I ask a question about what you
yes.
said? Need more than the Elliott invariant? Are you saying that the usual way the theorem stated is false?
No. Yeah, we need it in the proofs.
Oh,
So,
okay.
And the thing is that we classify inclusions. So we classify inclusions of C-star algebras, and that's and then when you apply this to essentially to identity maps, then you get classification of the Z-star algebras. But I didn't come to talk about classification. I came to talk about something else, which was the invariants. So if I wanted to do some sort of algebraic K1 of a C-star algebra, what I would do is I would again look at all the unitaries in matrix amplifications, and then I would close up this or quotient out with the commutator sums. And this turns out to be, well, this is not right. This would be unitary algebraic K1, but very often, and in order to have some more, let's say again, computable invariants, what we do is we add some of the topology that we already had, which is that and then we put a bar here to indicate this, is that we take the closure of the commutator subgroups. This becomes a much more manageable invariant, and it turns out that we get part of our invariant that we use to classify inclusions of C-star algebras is that we've got this version of K1 alg. Oh, I should have given myself more space. We've got a map going into the K1 group, which actually is surjective. And we also have a map from K0, A tensor ZA2 that goes into here. And this is actually something that the map here is really canonical. It's something that most people will have seen when they first learn about like projections. It is that every projection is in one-to-one correspondence with a unitary. Take a projection, you can construct a unitary by considering 1 minus 2p. And this map here induces a map that plays a very crucial. And moreover, so I can show this was. So you can show that if well, let's pretend that A is this reduced groupoid C star algebra. So the obvious maps that go like this make the diagram commute. So there seems to be a very strong connection between things of this flavor with these invariants that we're using to classify C-star algebra inclusions. And this thing down here is not exact. I should just warn everyone, it's not exact. And one of the reasons why you shouldn't expect it to be exact is because we've got some structure on the C-star level that we don't have in the topological full group. And more or less what I decided that I wanted to call this is that we've got scalar unitaries. We've got circle values. And for instance, if I took something as basic as the complex numbers and wanted to compute this is just the circle that you get out of this. You really would expect all of these circle values to be living on the C-star level, but not up here because we haven't added any circle coefficients. And one thing I was wondering, because we don't only have a map like this, we also have a map from K0 tends to Z mod n. What we do with Z mod n is that we map to, we could consider, let me just mention, we could think of this as being -1 times P plus 1 minus P. And then I just tweak this -1. So if I had, say, P tensor K, where this belongs to Z mod K, Z mod N, instead, I would map this to the class of the root of unitary 2 pi I K over N times P plus, and then just 1 minus P. So this gives something on the C-star level that we don't actually have groupoid level. And I've been wondering, is there any way you can add these circle coefficients on the groupoid level and maybe get a topological full group with some circle coefficients as well? Maybe something like a twisted groupoid. If you look at, for instance, just the groupoid with the canonical twist, can you use this canonical twist or maybe a non-canonical twist and maybe consider some like topological full group-ish type of thing that also has these circle values where you would actually get maybe maps from the zeroth homology group times Z mod n into this. I don't know. That was the brainstorm part of my talk, and I think I'm going to end with that. Thanks.